a bit going into the details. Let's see. I'm sharing the whole screen. Is it not coming there? You said what? Okay, but you say it's here. It said like I'm sharing the screen already, so I think it's fine. And like anyone can join and check and just let me know if it's not coming. Okay, so this one, in this, we see a bit more advanced of what we have seen. We would be going into the system level view. So let's go. And in this, we see the ALU. Can you just guess what that would mean? Logical unit. Okay. And what would be the CU? Control unit. And what would be the IO? We all know it. Input output. So we all know that this is the CPU. It would do with the arithmetic and logical operations, the control operations, also the clock. The clock determines the speed of processing. And we might also see the name called bus. It's like the way of transporting the information or the instruction. So control bus is for the control information. There are like three of them: control bus, data bus, and address bus. Address bus is just for transmitting the address. Control is just for the control information, and data, it's like the either way around. It can go to and out. Yeah, it is. It is like the overall view. It's the general view of a microcontroller. So we will see like what is within the microcontroller. We said like there is a processor. We said there would be a memory. We also said that there would be some ports to connect. Yes. I didn't get you. Cross topology? Bus. Yes, it's like, yeah, we can say it's a bus topology. It's like a general view, which shows what is within. There would be more detailed one later. This is like a general view. You will see many versions of the same. It's just to show you what are the components that's coming within. Again? Yes, control is usually given in one direction. We cannot control it both ways. So control is one side and data is usually both ways. And address bus is also usually single. We will see that in the coming slide. So for now, just note the names. I'll take my notes. Okay, so the next slide here, we will see much detail to each. So here we have, okay, we have the control unit as we saw. We have the ALU, it does with the calculations. Control unit is for the control operations. And registers. Registers is usually like a very, very short-term memory. It's like to just like hold but lose it at the same time. It's like a very short-term memory. And we would see how they are coming in line with the process flow. We will see. For now, just look at the names. I have a paper where I can write. I have the notes for you. I'm checking where I kept it. I have all the details. Notes for you. I will be sharing this also. So here we saw that within the CPU, we have the control unit, we have the ALU, we also have registers for now. as like sometimes when you come into the university, they give you a logbook. Yes, it's just for the short term. Just imagine like that. And in that, you have things like program counter, accumulator, MDR, MAR, CIR. Now, these are all like short term memories. For now, just understand that much. We will come back to the same slide again. And also, we have the main memory here, which is called as the RAM and ROM. The next one. So here you see we have the different names like registers, cache, memory, flash disk, traditional disk, and the remote secondary storage. So you see which is on the top, registers and cache. So these are the memories which is in the top of the peak of the hierarchy. So you also see something like this, one cycle, approximately 10 cycles. This symbol means approximately, the curve. So one cycle, then you say like approximately 10 cycle for the cache. So cycle means it's something like the speed. It just need one cycle to finish its task. It's like very speed. Cache little bit slower. Main memory again a bit slower. So this cycle means how much speed it has. So you see to the left, faster access, but they are of higher cost. So as you move up, they are faster but higher cost, and as you move down, they are less faster and lesser cost. And you see the top three of them, you call it as primary storage, and they are volatile. You know what is volatile in normal language? Like we have perfumes and they always say keep it closed, or you have sanitizer. Yes, you have to always keep it closed, otherwise what happens? It will go into the air and evaporate. No, volatile means like it evaporates and goes. It's just like for the short time, temporary. Yes. So volatile means they are very temporary. It's like for a very short time. If the power goes, then memory is erased. But you see something like down the secondary storage, which you call at the volatile, non-volatile. They stay. Non-volatile means they just don't go out, even if the power is cut off. So the examples are flash disk, traditional disk, and remote secondary storage. Example, the internet. You can even store that. It stays even if your power goes. So these are the different kinds of memories, memory hierarchies. You see registers in the top, volatile ones in the top. They are faster, higher cost, and the ones down, they have slower access but lower cost. Again, we are going deep into the type of memories, which we will see again much in detail. So we saw this. We saw like the CPU does with the ALU, CU control operation, and it has the clock. CPU has the registers. And now we know that registers are something like volatile, faster, and there are other memories as well, memory units as well, like flash disk, traditional disk, etc. Now, this is something that would clear most of our questions. You see, there is an arrow that goes to the right and then it goes to the left. So we can say like it goes to the volatile stage, non-volatile. So it goes this way. So what is happening? Cache means it is temporary. So what was in the top of the triangle? Register. Then it's cache. So which is closer to the processor? Register. So how does the data enter and leave the processor? Through the registers. And after register, we have the second component, which is called the cache. So data would go from register to cache to RAM to the secondary memory, and then again through this way. So processor works on the input from the registers. That much is okay for now. Now, to explain it a bit nicely, let me see if it gets copied. This is something that we need to understand. So I'll try to paste it here. Oh my, no, it's not coming. Okay, I will draw it here. Yeah, thank you. Who is giving me the good ideas? Sometimes even if we know, it will not come to our minds. Thank you. See the lower, I hope so. The lower part of my screen is stuck. Doesn't want to work. Um, Okay. So let me write a few points so that it would be easy to learn. Now, non-volatile ones, what do we call it? We can call it as like the storage ones because they are not going to be erased. Non-volatile means they just goes away when the power is off. Power is off. So that we know first point when we look in the figure. Now we know that this processor works on data from register. So it is through the register that the data enters the processor. Now, you see here, we have something called as the HDD, SSD, NVMe. And can we say like what is the HDD? Yeah, hard disk drive. So these are again the examples of the storage devices. SSD, NVMe, it's in the name here, non-volatile. You see the name at the top? So it comes from that, non-volatile, ME, memory, express. So we have like three kinds of storage which are non-volatile: hard disk, solid state drive, SSD, and NVMe. Now, like we can choose any of them. So the first one, hard disk, we choose like when we go for the cheaper option. It's cheaper and huge capacity. And also, yeah, it's low, it's fragile. Fragile means easily breakable. But when we go for the solid state one, it costs more. Cost more. And that's it. So it's like almost the same, but not as fragile as the hard disk. Now, faster, yes. Cost more, faster, yes. Faster. And the NVMe, yeah, it's 6 times faster. Smaller. Okay, smaller. So we would prefer that if we have a lot of money. And it is like mostly used when the money and the cost is like okay and for fast application. So that's it. So you see something called as non-volatile, they are the storage ones. So it is from there, if even if we connect, it goes how? It goes to the main memory, RAM, and from there it goes to the cache, then to the registers, and after processing, it comes to the register, it comes then back here to here and to the any of them. So this just says the memory organization or the data flow. So data flow, and it shows the memory organization. So what do we learn from here? We learned that it is through the register and then to the cache, then to the RAM, and then to the non-volatile one, the data flows. So this much is clear, I hope. Is it okay? Now, So next one, we are going again, like learning little by little and then going to the main core. So in CPU, we have the registers, as we know now. We have the arithmetic logical unit and PC. It's not the PC that we know, it's the program counter. So this is one additional component that we are seeing, PC, program counter. And what do you think the use of that is? So let me write it. So we have something called as the PC. PC is the program counter. Now, the program counter keeps track of what instruction to do next. So keeps track of what? Keeps track of the instruction that we should do next, that it should do next, not we. So program, you see, it's not like something, it's program. So program counter keeps track of the instruction that it should do next. It's also like next, like not like storing something, the previous one. What should do next? It would have as the instruction over there in the program counter. Now ALU, we know. What was ALU? Arithmetic logical unit. So just writing that, what does it do? Does math and decisions. So we should know what each of them would do. Now, keeps track of instruction that it should do next. Let's see what it actually means. Now you see, you have this memory, and if we have some kind of address in here, for that, for saying that, I'm going to the far end of our lecture. You see, program counter, you see here 0, 1. Can you read this red line? 0, 1, XX means whatever, whatever. If it is 0, 1, what will it do? It will load accumulator with contents of the address. So we would have also an accumulator coming into the scene. If it is 0, 1, it is the instruction that it should do next. So in the program counter, if we have something, some numbers, according to this, it would do it the next, not right now. It has the instruction that it should do next. That's the point. So 0, 1 means what should it do? Load the accumulator. It would do in the next step. So this step, it would not do it right now. It would do later. So see, if it is 0, 1, what should happen? It should load the accumulator. Where's the accumulator? Here. So this content would come, it is fetching, it is taking, and it should put it here. So you see, it would come, it's like not showing, it's like we will see in the last stage. So program counter, it would do load the accumulator, it would put it in here. It's not like do it right now. It's for the next step. You see, while it is doing this, the next instruction is waiting in the program counter. So I wanted to say that program counter is what? It would do the, like have instruction that it should do next. There is some kind of waiting. What does it have? Instruction. You should have this in mind. It keeps track of the instruction that it should not do now, do next. Don't look at me like that. You all have to study this. You will have to study it. So just understand. Again, program counter has the instruction that it should do next. Like we are telling a small kid, don't do, don't do, don't do. We tell it 100 times so that it will remember at least like don't do something. So I'm telling it like 10,000 times so that you will have some parts in mind. Program counter will be there, by the end of the slide, and we'd have the instruction that it will do, not now, next. And the buses. Someone asked me what is a bus and how many types are there. There is like 3 of them. So you see, address bus, data bus, control bus. What is a bus? Set of wires, and it helps in the interconnection. Interconnection between what all? CPU, memory, IO. We know memory is of so much of types. CPU will have components inside, like the registers or the ALU, CU. But overall, who connects or who takes information to and fro? Bus. There is like 3 of them for the address, for the control, and for the data. You see, address bus, it goes from memory to the input, like from the CPU to the memory to the output, input output. While data bus, it's like interconnecting between all. Address goes from CPU to here. Control connects them, like gives the control instruction. Data is bidirectional. Much clean or much good one is coming in this one. You can see here. You see, data, it goes and comes bidirectional, the green line. Control, it's just like do it. It doesn't take back. It's unidirectional. Same way, for the registers, we could say, like you saw, it was bidirectional. It gives and takes also. So we can say for the registers, it gives and takes. For now, just understand that data bus is bidirectional. There is also 2 other ones, control and address bus. We will see how all of them works soon. So going back a bit, we saw here about some components, control unit, ALU, we saw the registers. Then we saw like they are closer to the CPU, closer to the processor, and they are far, but they are non-volatile, they are volatile. So they are close to the processor, but volatile. A bit far away, but stable and non-volatile. And then we saw that the CPU has the registers, ALU, program counter, and the program counter has a good role in that to store the instruction. Now, we also saw the bus, like 3 types of them. Now, the IO devices. So, IO devices means they are devices, and how does it connect? Through the IO port or IO circuit. So, to show that, let's look into the figure before reading. I hope I have it here. Okay, so you see, you have the processor, you have the memory, and you have the IO, like we saw just before in the previous one. You see, CPU, memory, IO. You might think why there is like so much of figure to just like make us understand. Again, the same thing. So again, CPU, memory, IO, CPU, memory, and IO, the 3 again. But we are saying like if we have an input-output port, we are going to connect to it the input-output devices, and they are also connected by the buses. Just normal thing we are learning. Now, here, this is something we would write again to know a bit deeper. So you see, you know what is serial port? 1 by 1, like they are standing in a line. What do you mean by the parallel port? So parallel port means this one. That means it's like parallel. So many, like they are marching. So many lines. Serial means 1. So for serial operations or serial communications, we will be using that port. Parallel IO ports, like we'll be using some of them together. Now, bus control, this is OSC, not OSU. OSC means the oscillator, like we saw before, the clock. I will write and tell you what each of them means. I hope I can copy now. You can't see? Can you check? I think like it's saying like you are sharing the screen in the top. You see in the top? Oh, it's here. If you see, I am saying like you are sharing your screen. I hope it's. Okay, so I'm taking this figure and I am going to explain a bit. So just make the correction that this is OSC, which means the oscillator. And as we know, CPU is the CPU, which is the processing brain. And so what happens first? We will power it on. Yes. And the oscillator, it's like OSC will give the clock to the CPU. And that is like we can say in like normal analogy or normal way, we can say it's the heartbeat of the CPU. So it has to be there for the CPU to work. Like we saw the rising edge. So that is something like clock to the CPU. It is coming from the oscillator. Now, that's how the first part. And what does it do? What does the oscillator do? It helps in synchronizing. Synchronizing means like having a rhythm of the operations, connecting them. So synchronizes all operations. So that's what the oscillator does. Now, from the oscillator, now we move to the CPU. We don't have to say it again, but we just say, what does it do? It processes. It's a processor. Processes. And you see, like this CPU has to get information from somewhere. So from where do you think that information would come? From the memory, yes? So here we have the bus. Like, let me draw with just this line, black line, okay? It's the straight line. And this is all connected to the bus. So CPU will get the information from the memory. So we will write here, gets informations, and that could be data and program. Instructions or data and program from memory. So it would be coming from this ROM and RAM. Now, this line, we can make it like a bit squarish. Oops. Learn how to draw. So here, this is called the bus. Yes, this board lines, I can call it by the name bus, but somebody has to control it. So that is why this. So it controls the data flow to and from and within. And that we could control using the bus. Now, so let me write the function of it. Controls, comma, manages data transfer. Pathways between the different units. Now, we are done with, like we know what this input ports are for and for the serial ports are for the connection to the external devices. Connection to external devices. Now, we have something called as the interrupt. So imagine now I'm taking the class. The head of the department comes and he calls me. What should I do? I should say, no, I'm busy. Or I should go. What do you think it's right? According to the interrupt world, I have to stop what I'm doing and I have to go to see him. So it's like interrupting. So interrupt means it would stop what it's actually doing and it would do what it's asked to using that interrupt control port. So interrupt control means you have to stop what you're doing and do what is instructed. So this one stops the normal cycle, normal process, and it would follow and follows interrupt instructions. So that's what I said. If somebody tries to interrupt and that guy or that boss, it's a boss, you have to like, okay, come in. You have to do it. So CPU works with the clock signals that comes from the oscillator. It deals with the data coming from the memory, RAM, ROM, and there is a bus control which would control the data flow. We can connect the input, output all through these two ports. And there is something called as the interrupt control, which would stop the present actions or present process and give attention to the one that is asked to do. And it follows the interrupt instructions. Almost clear? So for now, if you want to store, you can use the storing option. It's like if you want to, it follows the instruction. If in the instruction it is asked to store, you would store. Or if you don't want, then it wouldn't. Yes, if we want to, we could. So it's always set like may. If you want to, do it. So that one, it's like in the far away. Anyway, it would be in the volatile memory. If you want to push it to the storage, you can even do that. Now, this is done. So let's move to the slides. So we have some idea now. So as you see, what's the name of the slide? Atmega 328. And in the bracket, you have the Arduino Uno name. I was waiting for this name to come. And block diagram, it says. Let's go to the next picture. Oh, wow. You see, in the big one, you have the Atmega to a side. So what do you think this big thing is? The board. Yes, it's the board. The big one is the board. And in that you have the Atmega 328. Now, this whole thing, it comes together. This board comes with the Atmega 328, and that board you call by the name Arduino Uno. If you change the microcontroller, the name of this part changes. It would be Arduino something else. So if it is Atmega 328 microcontroller in the Arduino board, what do you call it? Uno. Is that part clear? That naming, we should know it. If this is the microcontroller used within the board, then the board's name is Arduino. And you can see that there is a power jack, like how do you give the power, and a USB port in, some other ports, and we can see that there is like the power options again, the reset, 5-volt, ground, and again, you see the PCs, program counter, and some pin out, so much of stuffs, yes? So what do you think? We can do so much of programming to the Atmega to work it to the way that we want. But just let's go up here. So this is coming in here. So this is the microcontroller. What does it have? Like we saw before, the CPU, the program memory, the memories in here. This is also a memory. That's the memory section. Then you have the timers. You know, why do you have some timer? Like you can, one basic operation, like you want to make it work for 5 minutes. You can set the timer. Or you can set the timer to make it turn off and on. So then you can set the timer that way. And serial communication means it is faster, like the Wi-Fi, the phone connection. It's like very faster. But if you want parallel, you will choose this part. And just listen now. I will be giving the notes. So you don't have to worry about writing. I will be giving the notes. For now, listen. But when I write so that I make it sure to you. The notes would be given. And the oscillator, the top one, the oscillator is for clocking the CPU. Now, why do you have the second one? It's like a backup one. So that's the overall view of the microcontroller. Now we are learning so much of things. Why? We will see again later. So we have the microcontroller, and the microcontroller is put in the board. Going back. So what did we learn until now? We learned about the overall view of a microcomputer, microcontroller, CPU, memory, the input output. We saw the different memory hierarchy here. We saw the data flow, and then we saw about the program counter. It would give the address. It would give the address for reading and writing. It would store the next instruction. We saw about the buses. We saw that we could connect the input output, and then we discussed this. So finally, when we come, we know that in a microcontroller, we have those many stuffs. And we put that microcontroller into the Arduino board, and we call it with the name Arduino Uno. Now, for that board, we could have digital input as well as digital output, also analog input and analog output. You see, here, these ports are usually for the digital ones, parallel communication, and these is also for the serial communication. Now, based on the coding, sometimes you might have separate ports for analog. Sometimes you can even code it to work with that. Are you sleeping? No, you cannot sleep. You have to listen. Otherwise, I will have to make you study alone. Threatening you. So here, okay, let's see. What are the other courses that you are learning this semester? This year? I was sitting and talking. What are other courses that you take? Only signals? Physics. Physics. Physics lab. Okay. So which course you like the most? This or that? I will make you say this. Okay. Okay. I wanted them to say signals and systems. You see, I wanted that answer. And in signals and systems, that's the other course that I'm taking. We always see waveforms. Yes? No, I'm saying I wanted you to say signals and systems. Why? In that course, you see waveforms. And those, they are not digital, they are analog. So real world signals, they are always like the waves. So if you want this guy to work with the real world, it should have analog ports. It has. If you want it to work with the digital signals, like processed one, it has. So that's what it says in the next slide. It supports digital input. It supports digital output. It can give and it can also take and give. So it means that the board is flexible. It has pins, which is allowing us to take real world signals. And also it can give analog signals for the actuators to work. Like if it is like a robotic arm, it can get the analog signal and make it work accordingly. So it is flexible. That's what we are trying to say. Now, some definitions. Okay, before that, you know that we have assignments, but the numbers may be 2 or 3. So, though you hear a lot of words like theory from here, in the assignments, the question will be such that the quizzes follow the same pattern. So it's like you don't have to study all the theory, just follow the assignment questions. It would help. For now, you are trying to understand. If you want, you can write, but I would provide the notes, follow the assignments, and you will be getting good grades. If just it's that your aim. If you want to understand as well, you can listen. You have to. Okay, now the next boring session, please listen. Instructions and instruction set. Okay. So it's in the name itself. Instruction set, it's like a bunch of flowers. It has. Now, instruction is like you give one flower to it, again one flower. So it's like instruction set means it already has a set of instruction to it, the microcontroller. And instruction is something that you give to it one by one. So it does something according to it. Just some definitions you are seeing. Every microcontroller and the processor within will have its own instruction set. It has. When we ask or when we give an instruction, it works accordingly. It has a set of instruction for itself. Every microprocessor inside a microcontroller has its own instruction set. Now, this is something good to see in this way. I hope it's good. So you see, like, maybe you will read it. Okay. Have you seen complex languages other than the Python? C. C++. More complex than that?
Sentence.
Huh?
Again?
Assembly. Okay. Again? PHP. Okay, you know about that? I don't. Okay. So we start, or maybe I just say I cannot generalize. You know assembly languages. I don't know. So we start with the high-level languages, which is much simple for us. But when it comes to the machine, it has to be converted to the assembly and then to the machine language for the machine to understand. So we type in the high-level languages. It has to be converted to the machine language for the machine to understand. So it just says that we are usually here. It has to be converted to this and then to that. Read later. So software level, coding and application program as our requirement. What is HLL? High level language. That's what we know. So we do coding here. And that has to be converted to this. See, converts HLL to assembly language. And that would generate the machine code. Who? The assembler. So HLL, the compiler does convert to assembly language. The assembler comes to machine language. Just understand, once we give the high level language, it has to be converted to the machine language for it to understand. So even though we code to the microcontroller or microprocessor, we do some software coding, it has to be converted to the machine code for it to understand. Now, you might have seen or heard about the gates, transistors, and to the much smaller level of silicon. So when we give the instructions to the CPU, how does it do? It's like with the gates, with the flip-flops, transistors, it goes to the micro level. So that's what it says in the last. CPU gets the information, it goes to the gates, and it comes to the level of the manufacturing silicon level. So it shows that it's like processed in the silicon level or the lowest level. So software, if it is in the software level, we know the hardware, like high level language goes to the machine code, and in the hardware side, it has to do the processing. It goes to the level of the transistors to do our processing. So the transistors, if it is like speedy or according to its manufacturing component or material, the process will be faster. So it all lies into that side, the material. Now, this one, you see, this is an example of high level language. Like we can type in like equation way. But when it comes to that, you see, we like give integer and we say, okay, x is equal to 2 times x plus 15. We can read it. We know it. Like it's 2 multiplied by x plus 15. But when it comes to the assembly language, you see, it doesn't make much sense to us. And here for the machine code, no sense for us, but sense for the machine. It understands. So this slide says that whatever code we give, it's understandable for us, but has to be transformed for the machine to understand. Yes. Again? No. We are seeing from the two perspectives. From the software side, we convert into the machine code. Well, it has to go to the hardware level. Hardware, that processing completely stops with the transistors or in the silicon or the, like what you say, in the material level. Like who does the final stage? It's the transistors, or you can call it as the silicon.
Assembly language just compile like the Java, the computer. Yeah.
It's like halfway, middle way.
So it's compared from a Java language to machine code.
Yes. I don't know what Java means. I'm not in the Java yet.
Just
I'm not a one to comment on that. I don't know Java.
Don't have to understand that.
No, it's just an example. We don't have to. This is just an example. As I said, now your part is to listen. Listen, understand. What you have to learn, I will tell you in the assignments. Well, you should just go through your slide, know what it means. Like in this, what you said, in this century or in this time, nobody is asking you to like learn. You have to understand. When you understand it clearly. That's it. What you have to learn is the second part. It would be given as an assignment. I will also guide you, like after the class, I will tell you what should be learned for the exam. For now, understand. That's it. Now, this is the almost time. Oh, I will miss you all. I haven't finished. No. Don't go. 2 more minutes, okay? Otherwise, I will feel guilty. I lost almost 45 minutes today. With this, I will finish. So, be happy, okay? You are going to leave in another 2 minutes, but don't have to take the attendance. We will learn later. I will torture you in the next class. Well, you have like how much slides left? 4, 5. From the 24th slide, you might think it is something difficult. It's just the like what we have learned until now. 4 more slides left. Yes. It's already there. I have to upload the. It's not there? Oh. Oh, let me see. Oh, only the first one is there. Okay, I'm sorry. I will upload it.
I think that the
Okay. Because you see, I'm going to take a while. I want you to write your names, girls and boys, because my car would leave at 5:30. I almost forgot the time. You have a paper that you could write your names? You have a paper? Okay, please write your name. Please make it fast for me. You have a paper that you could give me? Yeah. Fast, okay? And this. Yeah, the notes I would save it, and maybe in like half an hour while I'm in the university car. If you don't, please send me a few photos. Yeah, I usually but please, so that I will remember. There would be two, but it's usually like maybe 20 or 30. You would be guided to what you love and you have to get good marks. I know that's what everyone wants. There were? There were no questions, yeah. I know, but it's not fully with the other side. So you will get a clear understanding. I closed the recording. I didn't close the Teams.